Welcome to lecture 13 in our class on stochastic processes. We will talk today about Brownian motion. We will continue our introduction to the properties of Brownian motion. We will discuss the martingale properties, or a few martingale properties of Brownian motion. In particular, Brownian motion will be shown to be a martingale. And the second larger segment of today's lecture will be devoted to the characterization of Brownian motion as a Gaussian process. Gaussian processes is a certain subclass of stochastic processes which are very easy to describe in terms of effectively linear algebra expressions in the end, or operator theory, but they are rich enough in order to model an interesting variety of phenomena. And we will show that Brownian motion is an instance of such a Gaussian process with further specific properties. Okay, so let's recall what we want to understand as a Brownian motion. A Brownian motion is a stochastic process which is parameterized by a continuous time reservoir, so it's the time parameters range over the non-negative real numbers, which has the following properties. Namely, we want that for almost all realization of a path, that path is continuous. So with probability 0, we observe a path that has a jump somewhere. The second condition is that the increments of the Brownian motion of that process are stochastically independent. And this is formulated as follows. So if you pick yourself a collection of time points which are ordered, and you evaluate the Brownian motion at those time points, including time point 0 of the process, and then you consider all those increments. So it's the displacement that you observe relative to one of those subintervals of time which lie between two time parameters, time points. So x0 has a particular role as the displacement or as the initial position. And then you start evaluating the first displacement that you observe at time t1 relative to position x0. That's the first increment. Then you consider the next increment that was observed in the process in the time interval from t1 to t2, and so forth, until you arrive at the change of position, if you like, relative to the time points tn minus 1 and tn. So that's a sequence of random variables, and what you want is that these random variables are independent. And what this is supposed to say is that the jump, or the difference in positions, just paraphrasing what I'm not saying, is that the difference in position that you see between time 2 hours and time 1 hours is stochastically not connected in any way to the difference in position that you see when you compare the position at time 1 hour and 0, for instance. So it says that the pushes, so the net motion of that particle, say, or that system that you want to describe with Brownian motion, that the net change in positions, they are not in any way stochastically related. And finally, we want that each of those individual increments has a specific distribution, namely it's a standard distributed, a normally distributed random variable with mean value 0 and variance equal to the size of the time interval on which you do observe this displacement or this increment. So the increments alone are random variables which are independent, and they are normally distributed with a variance which is proportional to the time step that you do in the two respective observations. If these three conditions are satisfied, then we call the process X a Brownian motion. Now, if we are dealing with vector-valued processes, for instance, an RD-valued process, xt, then such a process is called a vector-valued or a higher dimensional Brownian motion in dimension d, for instance, if the individual coordinate processes of this d-dimensional process, so you have d individual coordinates, which you can evaluate separately, and what you want is that each of these individual coordinate processes are alone Brownian motions, and you want that the coordinate processes are independent. If that's the case, then you call this process a d-dimensional Brownian motion. If additionally you have that the process starts in the origin, then you call this process a standard Brownian motion. Okay, and now you could ask the question, to what extent is a Brownian motion unique? Well, there are different concepts for uniqueness, or for saying that two processes are equivalent. For instance, you could say that two processes are identified when the corresponding finite dimensional distributions coincide. In that regard, of course, since we have determined the finite dimensional distributions for the previous conditions, and we will show that in a minute, Brownian motion is unique in terms of finite dimensional distributions. And we can even say something stronger. We can say that even if there might be different ways how to construct Brownian motion, if you pass to a canonical representation of this process as a canonical process on the collection of continuous paths, then this is even unique in the sense that there's only one probability law on this collection of continuous paths, which realizes Brownian motion. So the statement here is that all standard Brownian motions induce the same law if we pass to the corresponding path-valued random variable, which associates each realization of randomness to the corresponding path, to the corresponding trajectory. So, in other words, if we have any Brownian motion, x, which is defined on a probability space omega fp, then we can consider this as a map which maps each omega as into the corresponding element of continuous functions from the non-negative real line into the state space R. So if we consider this Brownian motion, or a Brownian motion, which we have just identified by checking all these three conditions, if we have such a Brownian motion, we can consider the corresponding map that associates to each realization of randomness, to each omega, the corresponding continuous function, which is the trajectory defined through this choice of a random parameter omega. This will then be a random variable. This x dot random variable will be a random variable which assumes values in the set of continuous paths. And this random variable is in fact measurable if we equip the set of continuous paths with the Borel sigma field, which is induced from the topology of locally uniform convergence. And so we basically have produced now a measurable space, the canonical path space omega tilde of continuous paths, which is equipped with this Borel sigma field, and any whatsoever Brownian motion induces a map from its probability space into this omega space, omega tilde. So x dot is a map which maps the given abstract omega into omega tilde, and therefore we can talk about this law of this random variable. And what it said is that any Brownian motion, whatever you take, produces in the end, if you consider it as a path-valued map, the same law on this canonical path space. Well, why is this the case? Well, we have to check that whatever we insert into this map, whatever initial probability space we were starting with, the corresponding statistical description, which is in the end the corresponding law, that this is the same regardless of the actual model that we were starting with. And so in order to check this by the usual arguments that the sigma field is generated by cylindrical test functions, etc., on this canonical path space, it suffices to check that if we evaluate this continuous path valued map by a sequence of evaluations of the path at a collection of time points, that this evaluation is always the same regardless of the probability space that we were starting with. Okay, so let's assume then that we have a Brownian motion X, which is defined on some probability space. Then we can, in fact, ask for the finite dimensional distributions, and asking for the finite dimensional distributions is the same as evaluating the expectations of all those combined product evaluations where the choices fi are any measurable function on the Euclidean space, for instance, on the Euclidean line. And in order to insert what we know about the finite dimensional distributions according to the definition of Brownian motion, we try to represent the same numbers which appear in this expectation as numbers which come from increments. So for instance, we can write this evaluation at time t1 as the increment between time t1 and time naught, because here we want to deal with standard Brownian motions, so therefore x naught is naught, so therefore this minus x naught is effectively not anything at all, because it's just 0 there. And we can continue like this for the evaluation of xt2. xt2 we can write as the sum of the increments that we make in the transition from naught to t1 and from t1 to t2, plus x naught, of course, which again was 0, and so forth. So we do this for all these evaluations, and for the final evaluation, we get a sum of n increments. And now we have managed to represent this expectation of these different evaluations of the Brownian motion as an evaluation which involves only the increments, but we know how the increments are distributed. The increments, this collection of increments which effectively appear here in this expectation by assumption on Brownian motion, represent independent, normally distributed random variables with expectation 0 and variance proportional to the corresponding time lags. So for instance, this random variable here, xt1 minus x naught, in distribution, and that's all that we need for computing this expectation, is the same as a standard normal distribution with variance 1, but multiplied with square root of t1, because the square root of t1 in variance gives exactly the t1 variance that we want for this, for the statistics of this random variable. Having fixed a representation of this first increment, which we also have to insert here, we now have the second increment. But the second increment can be represented in a similar fashion by a properly scaled standard normal distributed random variable xi2, but again scaled with this square root of t2 minus t1 in order to get the proper scaling. And xi1 and xi2 need to be independent because they represent the independent increments of the Brownian motion, and so forth. And for the nth evaluation here, we obtain the sum of these scaled random variables that we had before. So this is the expectation that we have to compute, and this expectation now involves only n independent standard normal distributed random variables. So we see that this expectation actually is independent of and has nothing to do and loses all the information about the concrete probability space on which the initial Brownian motion x that we were starting with is defined. So all these finite dimensional evaluations or distributions are the same, and therefore the induced law on path space is the same. And therefore the law of a standard Brownian motion, interpreted as a random variable which assumes values in the collection of continuous functions on the non-negative real line with values in the reals, this law is uniquely determined. And the corresponding law, this probability measure that we have just effectively introduced by talking about this law, this probability measure has a name, it's called the Veena measure, and it's now uniquely determined. This is the law of a Brownian motion that starts in the origin, interpreted as a probability measure on the collection of continuous functions. And in a similar fashion, we can introduce now the Veena measure for a Brownian motion that starts in an arbitrary point x from the real line by exactly the same argument. Exactly this Veena measure with starting point x is uniquely determined. And in this respect, if we work with canonical path space as our favorite probability space on which we represent stochastic processes, then we can define the process Bt mapping from canonical path space into the d-dimensional Euclidean space or just into the real line by defining that Bt of omega, when omega is one of those paths, is just the evaluation of omega at position t. Then, if we endow this canonical path space of continuous paths with the Veena measure for a Brownian motion starting in x, then this Bt or Btx process is another instance of a Brownian motion starting in x, and this is what we shall call the canonical model for Brownian motion starting in x. We call it the canonical model because this is, in a way, the object that lies at the bottom of all other models of Brownian motion, and we can project, if you like, every model of Brownian motion or every instance of a Brownian motion to this universal parametrization. Okay, and obviously the difference between this canonical Brownian motion starting in x and the canonical Brownian motion starting in 0, a standard canonical Brownian motion, is just that you can obtain the shifted or the new Brownian motion with a different starting point by just applying the constant spatial shift by x, by the space position x to all of these paths in order to construct a Brownian motion that starts in x from a Brownian motion that starts in 0. And you will see that the statistical properties of the Btx process will be exactly as you want, and it will be a realization on the canonical path space. Okay, so that's for now regarding the uniqueness and what we actually do understand by a Brownian motion. So we have introduced this now as a representation on canonical path space, but not always you really need to go back to this universal representation. In many cases, that is not necessary. You can do computations with a Brownian motion right away. But we want to emphasize that there are many, many Brownian motions, but there's only one canonical Brownian motion. And that's the canonical Brownian motion, which is obtained as the evaluation process on canonical path space when you equip the canonical path space with the corresponding Veena measure. Okay, now I had promised that I want to show that the Brownian motion has martingale properties, or is in fact a martingale relative to its own filtration, and that's the subject of the next proposition. In fact, Brownian motion is a martingale. Okay, we can prove that quite easily. Okay, we want to show, so the fact that this is an integrable random variable follows directly from the fact that this is the standard Brownian motion at each moment of time follows a normal distribution with mean 0 and variance t. So integrability is not an issue, or so evident. And we want to check the martingale identity. Namely, we take the process at time t, and we want to compute the conditional expectation given the sigma field induced by the process up to time s, where s is smaller than t. So that thing here is fxs. Okay, and we again try to go back to the increments. That will be our strategy for many computations, at the beginning at least for Brownian motion. So we do that by inserting a 0 here, which is written as a plus xs minus xs. We have not changed anything except for inserting a 0. Now that's the conditional expectation of a sum of two things. So it's the sum of the conditional expectations, but the xs process, or the xs random variable, is obviously measurable with respect to that sigma field, so it is not affected by the conditional expectation. And the second summand remains. It's the increment which we want to compute the conditional expectation of given the past. Now, the sigma field generated by all the possible realizations of the trajectory up to point u is the same as if we consider the sigma field which is generated by the increments of the trajectory towards the initial position and the initial position. The information of these two sigma fields is the same, or it's just the two sigma fields are the same, because any event that can be formulated in terms of the xu's can also be formulated in terms of these increment random variables and the x0 random variable. Okay, so therefore I can write this sigma field just as good as like this. I'm doing it in order to understand that this xt minus xs is one of the increments that appears in the independence of increments condition in Brownian motion, and this is a collection of all kinds of other increments, but each of them is independent of the increment that is here in the conditional expectation, and also x0 is independent of this increment. So this, in the end, here the sigma field on which I want to project is a sigma field which is generated by independent random variables, independent from the random variable of which I want to take the conditional expectation. And in this case, we know that the conditional expectation of that independent random variable is just the full expectation considered as a constant random variable. But now the expectation of this increment is the expectation of a normally distributed random variable with expectation 0, so therefore this whole thing is a 0, and I'm left with xs, which is what I wanted to prove. Namely, you wanted to prove that the conditional expectation of xt given the sigma field generated by xs up to moment s is xs. So in fact, it's a martingale. I can also construct another nice martingale, which is not quite as straightforward, but also not so very difficult, which comes along with Brownian motion. Namely, if we know that x is a Brownian motion, if we know that x is a martingale, then by Jensen's inequality, xt squared, so the square process, is a submartingale. So it's a process which has a positive drift. And we can ask for something like a dupe decomposition. Is there something that we have to subtract in order to get a martingale? And that there is something, and the process we have to subtract to get the martingale back, the martingale property back for the xt square process, is now the process which is deterministic, and which is the process, just the identity in time. So the statement here is that if we have a Brownian motion, xt, then xt squared minus t is also a Brownian motion. We will learn later that this property already characterizes Brownian motion, by the way. So again, I probably was misstating the actual proposition here. So if xt is a Brownian motion, then xt squared minus t as a process in time t is also a martingale relative to that filtration. Okay, why is that true? Okay, so we take the squared of our Brownian motion and want to compute the conditional expectation given fs. And the same strategy applies. I want to write the xt thing in such a way that I see an increment. So I insert inside the square the 0, which I write as plus minus xs. Then I have a sum of a difference and an xs in the square, which I square out by the binomial formula, which gives me this difference squared plus 2 times the difference times the xs plus the xs squared. All of this is inside the conditional expectation. I decompose it into the summons, get these 3 pieces for the conditional expectation. The first thing is just this first summand. The second summand is the conditional expectation of this product of xs and the difference, this increment. But the xs again is measurable with respect to xs, so with respect to fs, so it goes to the front. It goes as a factor outside of the conditional expectation, and I'm left with the conditional expectation of the increment, and it remains the conditional expectation of xs squared given fs, which again by measurability is just xs squared. Okay, so again by independence, the first of these 3 summands is just the straightforward conditional, it's just the straightforward full expectation, again by independence, of xt minus xs to fs. The second summand is a 0 because I know that x is a martingale, so this conditional increment is a 0. And finally I'm left with xs squared. Now the full expectation of this increment squared is the variance of this increment, and that was supposed to be t minus s by our condition on the Brownian motion. So I'm left with t minus s plus xs squared, which is not quite the statement that I wanted to see, but it yields obviously the statement because I can equivalently reformulate or reshuffle the different pieces of this inequality by subtracting the t term. And since the deterministic quantity inserted in the conditional expectation is just that this thing itself, I can just also just put in the t inside the conditional expectation in order to arrive at the statement which we have here. The conditional expectation of xt squared minus t given fs is xs squared minus s, which means exactly that xt squared minus t is a martingale relative to the filtration generated by x. So as I just said, we know that by abstract arguments xt squared must be a submartingale, and t, this t process, is therefore called the compensator because it's a process which I need to subtract in order to get a martingale back. So this is in a way like the decomposition. We have seen that xt squared I can also write as xt squared minus t plus t. Then this submartingale is decomposed into a martingale plus a term which is increasing over time. This is then our Doob decomposition of the submartingale obtained from squaring a Brownian motion. As I said, this largest part of today's lecture will be devoted to showing that Brownian motion is a Gaussian process. Gaussian processes are very nice and easy to describe, and we can do a lot of nice computations because they have a very nice algebraic representation. Therefore, it's very useful to know that the Brownian motion is a Gaussian process because it, as I just said, can simplify considerably certain arguments. And for that purpose, we shall introduce at all the class of Gaussian processes. And even for that, we need to understand a little more what we understand by a Gaussian random variable which assumes values in a Euclidean space of dimension d. Therefore, I have the following definition. A random variable x which assumes values in d-dimensional space, which you can always think of a random number generator, but it's not a random number which is generated, it's a random point which is generated, a random point in d-dimensional Euclidean space. That is called a Gaussian, so a d-dimensional Gaussian random variable, if the following is true, if for any fixed direction z, you project the generated point in direction z by means of taking the inner Euclidean product, so just the standard inner product of Rd, then this is, of course, a real valued random variable, but we want that this is a normally distributed real valued random variable. So whenever the projection of this random variable x onto a given one-dimensional space, which we do by taking the inner product of x with this direction z, whenever such projections are real valued normal distributed random variables, then the random variable x alone will be called d-dimensional Gaussian. We could also say, in yet another form, we could say whenever all linear applications, all linear maps of the random variable x to the Euclidean line, when all linear functionals of the process x are Gaussian random variables in one dimension, then we call this random variable d-dimensional Gaussian. And it will turn out that this definition gives rise to a class of probability distributions on d-dimensional space, which collect all possible distributions of such Gaussian random variables, and these will be, as we shall now naturally call them, the class of d-dimensional Gaussian distributions. And this will be defined as follows. Given a matrix A, which we shall call a covariance matrix, a matrix A, which is a d times d or d by d symmetric matrix, which is supposed to be positive definite, and given a vector m of dimension d, which we shall call the expected value. So given a matrix A and a vector m of appropriate dimension, then we can define a probability measure on all Borel sets of the d-dimensional space through the following assignment. Given a Borel set E, we define as the new measure, which we index by these two parameters A and M. We define a new measure, which is then a Gaussian measure later, by effectively again integrating a certain function over this Borel set E, where this whole expression that is obtained as the integral will be multiplied by a normalizing constant which is independent of E, in order to make sure that this assignment or that this definition produces a probability measure. So this inverse function, this inverse number which we have here in front of this integral is what we call a normalization constant or a normalizing factor, and I will discuss this in a minute, why this is the right normalization. But before we consider the right choice of a normalizing constant, we record that this measure that we introduce is following our standard or very typical definition of a measure in Euclidean space. It is obtained by integrating over the given subset E a certain function, and this function is of a specific type. It is an exponential of a negative quadratic form, which we evaluate on the integration variable x. And this quadratic form is obtained by shifting this variable x in space by the vector m, and then the corresponding shifted vector will be inserted into the quadratic form, which is generated by the inverse of the matrix A. This is the function as a function in x, which we need to integrate over the set E in order to define the size of the set E in terms of a measure. Of course, there is this normalizing constant. Before I discuss the actual choice of this normalizing constant, I show you the picture that you might have seen already. So here you have the case when d equals 2. It's a picture for how we define this measure in 2 dimensions. And we have the domain on which the 2-dimensional plane is here equipped with the coordinate axes x and y, and the set E is painted in red here. It's sketched as this red flat piece of the 2-dimensional plane. And if we want to measure the size of this red 2-dimensional domain, we have to integrate the green function, which is the exponential of the negative of a quadratic function in 2 dimensions, x and y. We have to integrate this green function, whose graph I have depicted in this green, which over the subset E, in order to compute the corresponding volume under this green curve. And this volume is what we shall interpret as the size of the green correction, as the size of the red set in the 2-dimensional plane. And why do we have such a hill here, such a mountain, such a beautiful mountain as a graph of the function which we insert here? Well, that's something that you will understand easily if you ask yourselves, what are the level sets of this function? The level sets, when is this exponential expression the same for 2 different x values? Well, it's the same if they lie on the same ellipsoid for the corresponding height. And so in the end we have these, the ellipsoid is effectively defined through the eigendirections and the eigenvalues of the matrix A to the -1. And so we have these stacked ellipsoids for the corresponding height, which determine the level sets of the function. Which is inside this integral. And this is why we see this kind of smooth and mountain, whose cross section are scaled ellipsoids, which are defined through the matrix A. And we see, in fact, that this is very much a generalization of the situation that we have in 1 dimension. So whenever we cut through this picture in a 1-dimensional or 2-dimensional hyperplane, which is perpendicular to the xy axis, which corresponds to picking a z, a direction z. So if I pick, if you like, a direction z, then I get a net picture. Oh, that's probably not nicely. I get a net picture in this z direction, which will be just a standard Gauss bell-shaped function in the z direction. So that will be the geometric content or the geometric background for what we will prove now. As for the choice or proper choice of this normalizing constant, we recall a little bit of linear algebra. Namely, if the matrix A is positive definite and symmetric, then we can do a spectral decomposition of the matrix A. We find an orthonormal eigenbasis of the matrix A, such that in the orthonormal eigenbasis the matrix is diagonal, and this can also be expressed by saying that there is an orthonormal matrix, orthogonal matrix, such that, and a diagonal matrix such that the matrix A has this representation as the product of the orthogonal matrix theta t transpose, namely times the diagonal times theta. And if we introduce the functions, the matrix C, which is the same change to this orthogonal basis, but in this orthogonal basis we apply just the square root of the eigenvector. So we multiply in the middle with the matrix obtained by taking the square root of the corresponding diagonal entries. Then this is again a symmetric matrix. It commutes with the matrix A, and C times C, so the square of this matrix is A. So this matrix C is a version of the square root of the matrix A. And this matrix will play a role in order to justify that this chosen normalization constant in the definition of a Gaussian measure on d dimensions is the proper one, is the right one. In order to convince ourselves of that, we want to compute the full integral of the full Euclidean space of this spatial bell-shaped function. And we do this computation in the first step by applying just an additive shift to the integration variable. That's a change of variables with an additive shift whose functional determinant is 1. So therefore this integral is obtained where no functional determinant appears. And the second coordinate change that I do now is that I write x as a c times y, where c is this square root of a. And this gives me a new integration variable y. And of course, at the expense of a functional determinant, which here, since it's a linear change of coordinates, is just one fixed determinant of c, which is of course the square root of the determinant of a. And by the fact that c times c, so c squared, is the same as a, if I put the c over here and use the fact that a and c commute, and so I find that this ends up in the identity in the interior of this bracket. So therefore the integral that I have to compute in the end is e to the minus y, inner product y over 2 integrated over the whole Euclidean space. But this expression here is then just the Euclidean norm of y squared, so it's the sum of the yi squared in the exponent, which by the property that the exponent of a sum is the product of the exponents, I can write as an integral over all these individual coordinate square functions, where since the product is the Euclidean product by Fubini theorem, I can write as just the product of these integrals with respect to the individual coordinates. But each of these integrals has the value square root of 2 pi, so since I have the product of d of them, I get this term, this factor in the power d. And I should not forget that I had the square root of the determinant of a for the second change of coordinates. So therefore, this integral here that I started with has the value determinant of a times square root of 2 pi to the power d. And this shows, in fact, that this choice, the inverse of this number, is a good choice for a normalizing constant, because if e happens to be the, if I want to evaluate the same expression for e equals to rd, then I have just convinced myself that the integral gives exactly the number that appears here as the denominator. So it's a 1 in the end for E being d-dimensional Euclidean space. So, as I have just said, this whole Gaussian measure in higher dimension is the generalization of the normal distribution in 1, the spatial dimension. And it can also be formulated and defined when the matrix A is not strictly positive definite, but just positive semi-definite, which basically says that in certain space directions I have 0 fluctuations. So then this curve collapses to an effective curve in lower dimension. And it is sometimes very useful when we do computations with such Gaussian measures, which are of course terribly important. It's sometimes extremely useful to do some computations using the so-called Laplace transform of a measure, in the case when the measure is a Gaussian measure. I recall to you the concept of a Laplace transform of a measure which lives, for instance, on d-dimensional space, d-dimensional Euclidean space. So suppose you have a measure eta in d-dimensional Euclidean space, then we can use this measure eta to define a new function lambda eta, which is called Laplace transform, which is a function mapping from Euclidean space of the same dimension as the measure is defined on to the extended reals, and it's defined as follows. For a given argument or position z, the Laplace transform at z is defined to be the integral of a certain function which involves z as a parameter when we integrate over the given measure with respect to the given measure eta. And the function which we want to integrate is the exponential of the inner product of the of position x with this fixed direction z. So this is this function, which does not necessarily need to give finite values all the time. This function is called the Laplace transform. So as a function, it's the function that is in our interest, not the value of the function in one particular point. We want to consider the entire function as one object, and this function is what we call the Laplace transform. Since I might encounter values z when the Laplace transform is not finite, I sometimes distinguish, or we sometimes distinguish, those positions z which actually lead to a finite value, and the collection of such points will be called the domain of the Laplace transform, and all others which produce an output plus or minus infinity. Right, and except for a definition, this proposition that we use in the sequel is that the probability measure is uniquely determined by this Laplace transform, which means that if you have two probability measures, eta and eta prime, so if you have two probability measures, eta and eta prime, such that the Laplace transform of eta equals Laplace transform of eta prime, then necessarily eta must be the same as eta prime. And the converse is obviously also true. So if two measures have the same Laplace transform, then the measures must be the same. Okay, so I said it's a useful tool, and I want to convince you of this in the context of Gaussian measures, and for that purpose it is very useful to compute the Laplace transform of a Gaussian measure to start with. So next proposition, given such a Gaussian measure with a covariance matrix A and an expected value m, then the Laplace transform for such an eta on a position z is the product of e to the z inner product with m times e to the minus z a z halves. I am hesitating because at this moment I'm not sure anymore, but we will have to see in a second whether that is actually really a minus or a plus. We will see this in a second when we consider the proof. Okay. Why is this true? Why can we compute the Laplace transform? Okay. We can, we try at least. Let's write down what that means. So Laplace transform of that Gaussian measure at position z is the integral of this exponent of the inner product when we integrate against the measure eta, and here is the measure eta, which is a weighted Lebesgue measure with this particular weighting function. Okay, I want to compute this, and for my first step is the same as before. I apply this additive shift in order to pass this plus m parameter operation onto this first component, first factor. So that was just an additive shift in the transition from year to year, change of variables if you like. The next step is that I decompose this this inner product into a sum of two inner products in which one of the two, the y, the integration variable, does not appear, and I take this component as a multiplicative factor in front of the integral because it does not affect the integral except for being a constant factor. Now, the next step is, probably one can do it in a more elegant fashion, but that's how I typically do it. So the next step is to write this inner product of z and y in an artificial fashion such that this A minus 1 matrix shows up again, also in the inner product here. And I do so by writing this identity function, which is acting in front of the y, as an A times A minus 1. And this A will be translated to the z to the first component by the symmetry of the matrix A. And now I see that I have something like a binomial formula, an incomplete binomial formula for the quadratic form, which is induced by the matrix A to the minus 1, where the term that I have here would be one of the two homogeneous terms, and here I have a mixed term where one of the two, where the other component, the other monomial, is AZ. So the completion of the square would require another negative part, e to the minus AZ inserted into the quadratic form, which is induced from A to the minus 1. So I'm multiplying and dividing by this term inside the integral, where the part with a plus will be used to complete exactly this square here, which ultimately produces an expression of this form inside the integral, and the term which is outside, which is not used for the completion of the square, is exactly this term here, which is in the front. So let me say it again. I complete the square, and completing the square, which shows up here, results in the full binomial term with an m tilde, which is given by this AZ, which is the homogeneous part which was missing in this incomplete square. And what remains in front of the integral is a new factor, which is the correction term for this completion of the squares, which is this part above here. Okay. And so, in fact, I have now I have a product of two terms in front of the integral. The first term was obtained by the additive shift, and the second term was a term which was coming out of the integral through a completion of the square. And the integral that actually remains is an integral of exactly such a shifted of an exponential of the quadratic form induced by eta minus 1 modulo a shift. This is now exactly an integral of the type which I had just considered before, and therefore together with the normalizing factor, which I had to write all the time, and which was there indicated all the time, together with this normalizing factor, this whole thing produces a 1, such that I arrive at the claimed formula, where in fact the right sign in front of this quadratic form is a minus. Okay, I look at this statement again, and I need to correct. So the right formula for the Laplace transform of a d-dimensional Gaussian measure is given like this, where in the second exponent we have a plus. And why is this true? Well, when I have to complete the square in the second last step of the computation, the term that is missing for a full square is the corresponding homogeneous term, which involves a to the minus 1 times az times az. This is the term which is missing with a minus sign. So by multiplying with 1, which involves the minus term and the plus term, I use the minus term for completing the square, and the term that remains is the plus term here, and that's then finally the second factor in the formula, which was to be shown. So the right statement here is that the Laplace transform of a Gaussian measure involves a plus for the quadratic form in the second factor. Okay. Before I give the statement of the next proposition, I would like to emphasize that this computation is correct for any dimension. So in particular, it's also correct for dimension d equals 1 when it deals with one-dimensional Gaussian distributions. Okay, and with this Laplace transform and the uniqueness of the Laplace transform, I can now easily prove the following statement, that if I do have a probability measure on Rd, then this probability measure is in fact a Gaussian measure with this covariance matrix A and mean value M, if and only if for all directions Z or vectors Z in Rd, the image measure of eta under the linear map LZ, which is just the projection in terms of inner product in the direction of Z, whenever the image map of eta under such a correction, whenever the image measure of eta under this linear projection in direction Z is again a one-dimensional Gaussian measure whose parameters are Z inner product M for the expected value and sigma squared being Z comma AZ for sigma squared for the variance. So in other words, let me say it again, a probability measure on the Euclidean space of dimension D is a Gaussian measure if and only if the linear projections of this random variable, or the linear projections of this probability measure onto any direction, give Gaussian measures in one dimension with the characteristics coming from which are read off in terms of inner product with the expected value M and the variance being the corresponding quadratic form induced from A in the direction Z. Okay, how do we prove this? Well, let us give a name to this projection into the direction Z of the measure eta. Let's call this eta Z. And we can identify the measure eta Z, at least theoretically, if we know its Laplace transform. So therefore we write the Laplace transform of this measure eta Z. Now if we know that eta Z is obtained by a linear projection through the as the image under the linear projection map, then we can apply the general chain rule formula for integrals and just write this as an integral with respect to the initial measure, where we have to replace in the exterior function, this s variable has to be replaced by the corresponding function, which produces the image measure, where we then integrate against the initial measure. This is just general chain rule. And now we have here in the exponent e to the t times the linear projection in direction z. But since this linear projection in direction is just the inner product, which is linear with respect to z, we can also interpret this as the exponent of the linear projection in direction tz of x. And we see that what we do here is nothing but the Laplace transform in direction tz of the original measure. So therefore we can relate the Laplace transform of eta t directly to the Laplace transform of eta. And therefore we can infer directly information on the projection from the Laplace transform of the initial measure and vice versa. Hence, if we know that the Laplace transform of the projected measure has a particular structure, of which we read off immediately that eta z by the one-dimensional application by the application of the Laplace transform to one-dimensional Gaussian measures, from which we read off that this is the Laplace transform of a one-dimensional Gaussian measure with the corresponding statistics or specification, then this is the same as saying that the Laplace transform for the initial measure on Rd is given in this form, which tells us, and since this is correct for any z, that this measure must be in d-dimensional Gaussian measure. So in other words, if the projected measure is this measure here, then this is the same as saying that the non-projected measure must be the measure with these specifics, just by this one-to-one correspondence between Laplace transform and measures, and the possibility to write the Laplace transform by using the fact that the Laplace transform is in fact already dealing with projections into one-dimensional subspaces. The next result shows that our initially very simple and naive definition of a multidimensional Gaussian random variable actually coincides with those random variables which are distributed according to a Gaussian distribution in this very specific form. So the statement is like this: let x be an Rd-valued random variable, then x is Gaussian, according to the very first definition, if and only if its law is given by a Gaussian distribution with certain parameters m and a. Why is this true? Well, if we assume that this random variable is distributed according to such a specific Gaussian distribution, then we have already convinced ourselves that the one-dimensional distributions are Gaussian. So therefore, this direction is clear. To convince ourselves that the opposite conclusion is also correct, let us now assume that x is a Gaussian random variable in the very first sense, namely that all one-dimensional projections are Gaussian. We want to convince ourselves that the corresponding law eta of this full Rd-valued random variable is given in this parametric form. Okay. From the assumption on x, we know that the Laplace transform of the one-dimensional distribution in a given direction z coincides with the Laplace transform of the Gaussian measure in one dimension. Hence, if we consider this integral here, and this is effectively in Laplace transform which deals with the projection of the random variable x in the direction z. And since we know how this one-dimensional projection looks like, at least we know what I mean by this is at least we know that this is a one-dimensional Gaussian random variable. We know that this Laplace transform, which we wrote down here, must be the Laplace transform of a one-dimensional Gaussian random variable. So there are certain parameters mz and a certain parameter sigma z squared, such that this expectation has this form. And that's correct for any t. And for some given mz and z squared, which will be given or which will depend only on z. Now this is an identity for a whole family of t's, and we can compare the identity which we obtain if we take the first derivative with respect to t at time t equals 0. So then on the left hand side we obtain the expectation of the inner product of x with z integrated against eta dx, and on the right hand side we get mz. But the left hand side is just the expectation of this random variable, which is obtained by projecting onto z. So we find that mz necessarily must be this expected variable. So mz is not anything, mz is the expected value of x in direction z. We can also take the second order derivative of the two functions which appear in this identity star on both sides. Then the second order derivative on the left hand side produces the expected value of x projected onto the z direction squared. And on the right hand side, if we do the algebra, we obtain the expected value of x in projecting z squared, this expected value squared, plus sigma squared z, which if we rearrange or solve for sigma squared z, tells us that sigma squared z must be the variance of the same random variable x z. That's very valuable information, because we can now introduce this m vector, which is just the expectation of this x process in the ith direction of this x random variable, and we can introduce the matrix sigma, which has the entry sigma ij defined to be the covariance of the ith and the jth coordinate of this rd valued random variable. Then obviously the expectation of x in direction z is just the inner product of this m vector with the z vector, and the variance of xz, if we write out what this means, well, this is the expected value of x inner product with z minus the corresponding expected value squared. These inner products are just sums over these different times I can write this in one sum and can take the square of this sum. Expanding this square of a sum produces a double sum in two indices, I and j, where the only random element here is the xi, but I can factor out the zi and zj and put in, and here this expected value is too much. Here I can factor out the zi zj, and I obtain inside the expected value the product of xi minus mi and xj minus mj. But this is then by definition of sigma ij zi zj. So it's the quadratic form induced by sigma evaluated on z. Hence, I can use or rewrite my previous formula by the identification which I have obtained in the following fashion, that the expected value of the exponent of e to the tz with the inner product with x is equal to et z inner product m times e to the t squared z sigma z. And if I evaluate this identity at t equals 1, if you like, I obtain exactly the Laplace transform for a d-dimensional Gaussian distribution. So in fact, X follows a d-dimensional Gaussian distribution where the parameters are M is the expected value of X and A is the covariance matrix of X. Okay, after these computations of Laplace transforms and the clarification of what we understand as a random variable in Rd, which is Gaussian, we can now define what we understand by a Gaussian stochastic process. So here comes the definition. A real-valued stochastic process which has some index set I is called a Gaussian stochastic process if for all finite subsets of indices the corresponding finite dimensional vector which is obtained by evaluating this Gaussian process on those indices simultaneously which belong to this subcollection J of indices, this joint evaluation of the vector of this stochastic process at those times, interpreted then as an Euclidean random variable of appropriate dimension, if this is Gaussian. And we have just seen what it means that a random variable is Gaussian. So we call a stochastic process with an arbitrary index set I Gaussian if all the corresponding finite dimensional distributions are Gaussian. For such a process, we introduce the maps M and gamma. M is the function defined on this index set I, which associates to every I the expected value of the random variable or of the stochastic process at time I. And gamma is a function in two variables from I, where gamma ij is defined to be the covariance of xi and xj. These two functions are called the expectation and the covariance function of x. In our previous considerations regarding Gaussian measures on multidimensional space, we find that the finite dimensional distributions, which are then all these Gaussian distributions, or this collection of Gaussian distributions of a Gaussian process, are fully determined by the function gamma and n. So, a Gaussian process is defined by the property that all finite dimensional distributions are Gaussian, and obviously all these finite dimensional distributions are characterized, therefore, by indicating the collection of covariance and expected values. Okay, and now we can finally come back to the actual matter of this lecture and of this part of our lecture series, namely back to Brownian motion. And we can now determine and fully describe a Brownian motion as a Gaussian process as follows. So a real-valued stochastic process which has the full non-negative real line as time parameter set is a standard Brownian motion if and only if it is a Gaussian process with the covariance function gamma in St, which is defined as the infimum of S and T, with an expected value function which is 0, and if that process has almost surely continuous paths. This is an equivalent description of what it means for a process to be a Brownian motion. Okay, why is this true, that this is an equivalent description? Well, let us first show that a Brownian motion is in fact a Gaussian process. Well, of course, we want to check the finite dimensional distributions. That's what we need to check for the Gaussianity. So we ask, what's the law for a finite collection of time points if we evaluate the Brownian motion at those time points simultaneously? Then by just the same consideration, that we did when we discussed the induced law of a Brownian motion on path space, we can write all these joint evaluations, or the statistics of these joint evaluations, through a stacked sum of independent, properly scaled standard normal one-dimensional random variables. But it is easy to check that a linear combination of independent Gaussian random variables produces again a d-dimensional Gaussian random variable, for instance, by using the Laplace transform. So therefore we see that in fact the finite dimensional laws of the finite dimensional distributions of a Brownian motion are Gaussian, and as far as these expected value function and the covariance functions are concerned, we compute the expected value of Brownian motion at time t, which we assume to be a standard Brownian motion here. That is the expected value of xt. We have already seen that Brownian motion is a martingale, so that's the same, this expected value as the martingale evaluated at time 0. But at time 0, this process is 0. So therefore the expected value function is a constant function 0. And for the covariance function, the covariance of two random variables which have expected value 0 is just the expected value of the product. And the computation of the expected value of the product of two xt and xs can also be computed by considering the conditional expectation of xt, if t is the larger of the two, first, to the sigma field generated by x, by the Brownian motion, to time s, by the martingale property. This is xs, so this expected value of xt times xs is just the expected value of xs squared, which is the variance of xs, and by condition on Brownian motion, this is just s. So we see that the covariance of xt and xs is just s if s is smaller or equal to t. This shows that a Brownian motion is in fact a Gaussian process with the given covariance and expected value function, and of course it has continuous paths by definition. Now conversely, if we do have a Gaussian process with continuous paths and which has this expected value function 0 and this covariance function s of t, then the finite dimensional distributions of this process are uniquely determined through these two data. And so we see that the finite dimensional distributions of x dot are the same as those of a standard Brownian motion. Hence, we find that x in particular has independent Gaussian increments, and of course x naught equals naught. Since we were assuming that it's a continuous process, we finally see that the process is a Brownian motion because it has independent increments which are distributed as Gaussian random variables with the corresponding variances, and it has continuous path and starts in 0, so therefore x is a standard Brownian motion. We finally come to the last result of this lecture, which deals with certain transformations of Brownian motion and which give back Brownian motion. So the statement is as follows: if x is a Brownian motion, then also the following four processes, namely xt plus s minus xs for t greater or equal to naught. So you restart time at a later moment of time if you subtract the position that was assumed by the process at time s. Then this new process is again a standard Brownian motion. Second, the negative of a Brownian motion is also a Brownian motion. Third, the diffusive scaling of a Brownian motion by a constant c is also a Brownian motion, which means that you multiply the Brownian motion by c and evaluate this at time t over c squared. Then this is also a Brownian motion. And finally, an interesting construction is that you partially reverse time, but multiply the process with larger and larger factor proportional to time. So the new process x tilde t is defined to be not at t equals 0, and for any other t, you define the process x t tilde to be t times x evaluated at 1 over t, which means that effectively for t becoming larger and larger, you insert smaller and smaller values of the Brownian motion, the initial Brownian motion, at smaller and smaller times. So in that respect, it is a partial time inversion that you do in the construction number 4. And the statement here is, again, that all these 4 different transformations of the initial Brownian motion are, again, Brownian motion. Okay, let's prove this now. For instance, why is 1 correct? Well, it's clear that this process has still independent Gaussian increments, because the increment statistics of this shifted translated process are basically the same. So the independent Gaussian increment property is preserved. It's again a process with continuous in time trajectories, and it starts in 0, so therefore it is a Brownian motion. I should also say that, of course, the statistics of these increments are also given by a normal distribution. Okay. Property number 2 is very clear. It's just the property that the inversion or the negative of a Brownian motion or the negative of a Gaussian random variable is again Gaussian with the same statistics. Property 3 can now be easily understood, for instance, by saying that this is effectively a linear transformation of a Gaussian process, and linear transformation of a Gaussian process is again Gaussian, so therefore this new process 3 is a Gaussian process. It has continuous trajectories, and it has a 0 expectation. So all this is correct. So what remains to check is that this process has the right covariance function. So we compute the covariance for 2 different time points, t and s, according to the definition of this transformed process. Then by the fact that this covariance is bilinear, the c multiplication factor goes to the front as a c squared, and then we have the expectation of these Brownian motions at 2 different times, and we know that the product of the expectation of this product is given as the minimum of the 2 time indices. The minimum of t over c squared and s over c squared is, of course, the minimum of t and s over c squared, so we see that the c squared cancel and we get minimum t over s. So therefore, this is also a Gaussian process with covariance function minimum t and s for the 2 times when I compute the covariance function. Okay, so therefore it's a Brownian motion. And finally, the 4th construction. This process xt tilde for positive times t is a linear transformation of a Gaussian process. So therefore it's again a Gaussian process. The expected value of that process for t positive is also 0. And regarding the covariance function of this tilde process, by expectation being 0, this is the expected value of the product of these 2 x tilde processes for these 2 different times. By the construction of xt tilde and xs tilde, this is t times s as the product of the 2 factors times the minimum of 1 over t and 1 over s, which is, of course, 1 over the maximum of t and s. So if that is the inverse of this is multiplied with t times s, what remains is the minimum of t and s. So as a consequence, we have a Gaussian process which has the right covariance function and expected value function. So therefore it's a good candidate to be a Brownian motion. But what needs to be checked is the continuity. By construction of the trajectories xt tilde for t positive and the continuity of the initial process x, we see that the trajectories of xt tilde are continuous in all times t strictly bigger than 0. What needs to be checked is the continuity of this x tilde process at t equals 0, which is initially or at the beginning not at all evident, because we evaluate the Brownian motion at later and later. Sorry, let me say it again. We evaluate the Brownian motion here. If we let pass t to 0, we evaluate Brownian motion at later and later times, and we multiply this whole thing by t, which is, of course, damping these growing Brownian motions. Yes. So it's by no means clear that this t factor, which converges to 0 for t to 0, is converging fast enough in order to guarantee that this Brownian motion, which is effectively evaluated at larger and larger times, is not growing too quickly for the whole thing to still converge to 0. Okay. But we can in fact prove this, that the process xt is continuous almost surely. So if we, for instance, restrict the tilde process to a time parameter set which ranges among all rational times, then we see that the process has the same, also the restriction of this tilde process to the rational times yields a Gaussian process. And it has the same statistics by the uniqueness of the law of a Brownian motion, by the uniqueness of law of a Gaussian process through the covariance function expected as the initial Brownian motion, for instance. So the law of these two processes, when restricted to rational times, is the same, and hence the probability for the event that the limit when we let tend t to 0 among all rational times, the probability for this event is the same probability, can also be computed by asking the same question for the initial process xt, because this effectively is a question about an event which is determined on the path space for all rational points. So here it is important to confine this limiting question to time points or sequences which converge to 0, of sequences of rational time points. And then this, let me say it again, this event which is described here is an event which is determined entirely by looking at this x tilde process at these rational points, on which it has exactly the same statistics as the corresponding x process. But for the corresponding x process, we already know by continuity that this event, that this limit exists and is 0, has the probability of this event is 1. So therefore this same must be true for the corresponding xt tilde process. Let me say it again, this is a property of the two processes when restricted to rational times. So hence we know that these almost every trajectory of this x tilde process converges to 0 when time tends to 0, at least for rational times. On the other hand, we know that outside of t equals 0, the process is continuous. So the trajectories are continuous, almost surely, everywhere, except possibly not for 0, but the continuity when restricted to the rational points together with the continuity of trajectories together implies that in fact the whole convergence of all possible, so the convergence is also correct for any sequence of numbers t tending to 0, regardless whether it's a rational or not rational sequence of points. So hence we find that this x tilde process is in fact continuous, and also in t equals 0, and therefore continuity is established, which finally allows us to conclude that this x tilde process is, in fact, again, a standard Brownian motion.